Welcome to part 2 of Group 2 Elements e-lesson. Without further ado, let us proceed. Before I proceed on to talk about how Group 2 metals react with oxygen, water, and their respective oxides with water and oxygen, please allow me to remind you that at this point you should be able to describe the physical and chemical properties of all the Group 2 metals. Please be reminded that at any one point you could stop the show and return to it. Now, I shall assume that you have been able to master Assessment Objective D as per described just now. So, let us proceed. Group 2 metals react with oxygen in the equation as written as above. So, when left in air, basically, Group 2 metals will react with oxygen in the air, and thereby forming an oxide layer. This actually accounts for something quite important, that is, Group 2 metals, as well as some other metals, after reacting with oxygen gas, will have a lack of reactivity. This is actually because of the unreactive oxide layer. What you see in the diagram there is actually what we consider a rusted nail. Actually, rust is the formation of an oxide. So, many a times, because we actually do want our metals to react, we want to store these metals in protective paraffin oil such that they do not come in contact with oxygen in the air. Therefore, next time if anybody were to say metals are extremely reactive, please make sure not to take it at face value and correct it for yourself and ascertain whether there is an oxide layer or not. One of the most interesting things that you learn during your periodicity is your period 3 elements reacting with oxygen and the flame color of their burning. Well, like it or not, you have to also understand the flame color in this chapter. Basically, most of the elements will burn with a very bright flame. Magnesium, in particular, and this is actually extremely important for you to remember, will burn with a bright white flame. It is a very brilliant color, and it is something that you are expected to know. Calcium is a bit more questionable. Sources say either it's brick red or orange. It's also a very beautiful flame. Strontium burns with a crimson red flame, and barium burns with a green flame. Now, what is most important for you to remember is actually magnesium's burning color. Also, if you look closely, most of the metals actually have a little bit of resistance towards reacting with oxygen. Beryllium in particular, I cannot show you the picture because it does not actually have a very bright flame, and also it is extremely difficult to react. So, once again, what is important to remember? Magnesium. So once again, this is the table, and explaining once more time, the reason why there are inert reactions is because of the unreactive oxide layer, which is formed when the metal itself reacts with. Now, just to go on to something that is not in syllabus, naturally, if you wish to proceed on, you can just click on next slide. However, certain metals do react with special reactions, and this is actually quite interesting. Magnesium, although I say it actually forms an oxide layer when it reacts with air, actually tends to have another reaction when it reacts with air, and that is the formation of magnesium nitride. The idea here is that there is a very exothermic reaction which actually allows even the very strong nitrogen-nitrogen triple bond to be broken in order to form magnesium nitride. Another two interesting reactions are the barium and strontium reaction with oxygen if they are reacting in excess. What happens is, due to the excess of oxygen, it tends to form what we call a peroxide. Once again, for easy understanding, the idea here is, in limited oxygen cases, there will be a strontium oxide, that is SRO. However, because there's excess oxygen, it can form SRO2. These peroxides are actually something of little interest, and if you have taken the pre-test, now I'm sure you can go back and try and answer your question. So, proceeding on, we would like to talk about group 2 metals with water. So by this point, you should be able to understand that with oxygen, it does form a very simple reaction. It forms an oxide and also the certain flame color. Now, with water, however, there is a little difference. Let's talk about magnesium first. Magnesium has different reactivities based on different temperatures of water, that is. So in hot steam, what really happens is magnesium will react to form the oxide. However, in water, it forms a hydroxide. So once again, in steam, hot steam, it forms an oxide, and in cold water, it forms an hydroxide. In actuality, the reaction in cold water doesn't occur for long at all. What really happens is, upon reacting with water, the magnesium hydroxide layer will quickly coat the magnesium metal, thereby forming a protective layer. This allows magnesium from undergoing any further reaction. Now, that is the focus on magnesium, so let's talk about the other metals. For beryllium, it's actually quite simple. There is no visible reaction when reacting with water of any type. Whereas for calcium, strontium, and barium, it reacts with water to form the respective hydroxides. Now, what really you can see here, based on what we have brought in from magnesium as well, is just that down the group, the metals react more readily with water. Beryllium has no visible reaction. Magnesium reacts best with steam, while calcium, strontium, and barium onwards, they react with cold water. So, as you can see in this little graph down here, we can just say that down the group there is increasing reactivity with water. So, this part, I would like to make a particular distinction. I am not talking about the group 2 metals reaction with water. I am talking about the reaction of the oxides with water. If there's any question, just watch ahead and you should be able to figure it out. For beryllium oxide, like barium itself, it has no reaction with water. Meanwhile, magnesium oxide will have a very slow reaction with water in order to form MgOH2. And similarly for the rest of them, they will also form the respective metal hydroxides. Now, this part has been taught to you during the early preview. That is, the reaction actually is more and more exothermic as it goes down the group. As you can see in your notes, calcium reacts to give off 64.5 kilojoules per mole, following that strontium and barium. That is, it becomes more favorable energetically to form the hydroxide as we go down the group. Okay, please remember, being energetically more favorable does not mean the reaction will naturally progress. This is from chemical energetics. Now that we have gone through all the reactions, I hope you have been able to see that in water, one of the common products that is being formed is the hydroxide, and therefore we also pay a little attention to the respective hydroxide. The idea here is that here we form the hydroxide, this is the general equation, and we want to compare solubility. One basic principle is that the solubilities will increase down the group. If you can see here, magnesium hydroxide is insoluble, following that calcium hydroxide and all the way down, it becomes more and more soluble. If the diagrams are of any indication, the idea here is that calcium hydroxide is often obtained as this wet solid. Meanwhile, barium hydroxide will dissolve very readily. The idea here, if there's anything to grasp from it, is that when solubility increases, there is increasing pH, because as we go down the group, OH minus will form more and more readily. So once again, with this little diagram, I hope you are able to understand that as we go down the group, there is increasing solubility and therefore increasing pH. And that ends the part on oxides and hydroxides. Please, once again, stop here and check. Are you able to perform assessment objectives A and B confidently? Assessment objective A refers to the reaction of the elements with oxygen and water. So, whereas B talks about the behavior of the oxides with water. as you can see in the diagrams represented down here. As long as you are able to get a little grasp of this graph, you should be able to remember things better. Firstly, from beryllium down to barium, the metals itself has increasing reactivity with water. Remember, beryllium does not react. Following that, magnesium reacts best with steam. Following that, all the way down, calcium, strontium, and barium reacts with water to form the respective hydroxides. Following that, we are also talking about the oxides. The oxides also have a tendency to react with water to form the hydroxides. And most interestingly, we also want to explore the hydroxide solubility because it is an indication towards pH. As with the previous assessment objective, I'd like to remind you all that if at any one point there's any question, you should immediately end the show and revisit those slides. These parts are particularly important. Before I go on to the decomposition of group 2 nitrates, I will remind you again that you should be going back if you have any point of non-understanding. Now, this part we explore the most interesting part of your group 2 metals, talking about the group 2 nitrates decomposition. Firstly, the idea of group 2 nitrates decomposing is really just I am breaking up the metal nitrate to form nitrogen dioxide, oxygen gas, and usually an oxide, which is based on the equation as shown here. Now, decomposition actually occurs less easily as we go down the group. I would like to refer to the other PowerPoint slide that you have downloaded that has, like lovely for most of you, Miss Jane Slim's voice, and it will depict very, very beautifully and pictorially on why group 2 nitrates decompose less easily down the group. Now, our final slide before the summary. These are some points on group 2 metals as well as how you can use them. This is in the syllabus, therefore please try to remember at least a couple of them. Magnesium oxide is used very favorably as refractory materials. I believe you have seen all of this in your block test questions before, so please be reminded. To be a refractory material means that you must have a high melting point in order to withstand the great fire within a furnace. Magnesium hydroxide, on the other hand, is actually what you commonly use in your toothpaste, as well as in digestion medicine. If nothing else, I guess most of you can actually go and watch TV and remember the stalker advertisement of the Colgate dentist. Calcium oxide and calcium hydroxide are very commonly used as fertilizers because of their alkalinity, which allows them to get rid of the excess acidity within the soil in order for plants to grow more favorably. Calcium carbonate, on the other hand, is used as cement, and calcium sulfate is used for what we call plaster of Paris. This slide, please take some time to go and remember most of them. Some things are quite easy to remember, and some things are more important to remember. In particular, please remember magnesium oxide as refractory lining and magnesium hydroxide as toothpaste or indigestion medicine. Congratulations! You have finished your e-lesson on your Group 2 elements. Once again, to summarize everything, we now talk about, firstly, the properties which we have went through in great detail. And what do we concentrate on this vast table? Firstly, we have talked about the radii. Radii is increasing down the group because as we go down the group, there are more shells, there's greater screening effect, and therefore the electrons are further away from the nucleus. And based on the increasing radii down the group, we then go on to explain the decreasing melting point. As the radii increases, which is to say, as the attraction of the cation to the sea of electrons decreases, the melting point decreases because metallic bonding is becoming weaker. And then, following that, we talk about the E0 values. As we go down the group, the electrons are less and less attracted towards the nucleus. Therefore, they oxidize easily, therefore, their reducing power increases. That is to say, the more negative the E0 values are, the stronger the reducing power of the group 2 metals. So, to summarize everything once again, from beryllium down to barium, the radii increases, the melting point decreases, and the reducing power increases. The next important thing to summarize is the reaction of the metal with oxygen. Now, as you can see in this reaction, metals react with oxygen to form the metal oxide, which following that we talk about the protective layers. In a table, you can see these are the color of the flame. Once again, the important thing to remember is the reaction of magnesium burning in a dazzling white color. Following that, we have mentioned the group 2 metals reaction with water. As you can see in the summary, beryllium will not react with water, magnesium reacts with cold water and steam, and the rest of the metals all react to form the respective metal hydroxide. Once again, as a reminder, the metals will have increasing reactivity as we go down the group with water. Thus, we have talked about the group 2 oxides with water. Basically, beryllium oxide, like beryllium metal, will have no reaction with water, and with the idea of increasing reactivity down the group, magnesium oxide will have a slow reaction and the rest of the metals will just react quite normally. However, this time around, with even greater detail, we can use the delta H value to compare. Lastly, and most importantly, we have talked about the decomposition of the respective nitrates in order to form nitrogen gas, oxygen gas, and the metal oxide itself. Here, we have to talk about down the group the thermal stability. So, to summarize it in a table format, down the group, there is an increasing cationic size, as we have talked about in the earlier segment, which is ionic radii increases. Now, as that increases, the charge density will decrease. And therefore, once the charge density, that is, the ability for M2 plus to pull things over, decreases, the polarizing ability will decrease. So, if the nitrate gets less distorted, the idea for nitrate to have to, inverted comma, break into O2 minus and other components will become weaker. And therefore, the NO bond will not weaken as much, and the decomposition will occur less easily. Now, in words, these are obviously a bit difficult to understand. Therefore, in the next slide, you will see a couple of diagrams, so I can go through these points again. However, for greater explanation, please refer to the other PowerPoint slides that is attached in your e-lesson. So, as you go down the group, decomposition occurs less easily. That means the nitrates tend to stay as nitrates. The thermal stability will increase, and therefore the decomposition temperature will increase. So, in a progressive format, we once again look at the decomposition of the group 2 nitrates. As we go down the group from beryllium down to barium, there is an increase in the cationic size. This means that because the radius is increasing, charge density, which is proportional to charge over radius, will decrease as we go down the group. That means that barium has a poorer pulling power than beryllium, the polarizing power that is. And if the polarizing power of the cation decreases down from beryllium to barium, that means that barium cannot distort the nitrate anion as well as beryllium does. And what does that mean? That means barium cannot weaken the bonds within the nitrate anion as well as beryllium can. That is to say, once again, if I cannot weaken the bond of the nitrate as well, that means that I cannot cause decomposition as well. That is, barium nitrate will have less of a possibility of decomposing into the nitrogen dioxide and oxygen gas. And this is also meaning to say that barium nitrate is actually more stable because it decomposes less easily. And this would mean, of course, that the decomposition temperature of barium nitrate is higher than strontium nitrate, which is higher than calcium nitrate, higher than magnesium nitrate, higher than beryllium nitrate. Diagrammatically formed, this would be it. As you can see, the idea of decomposition is the M2 plus is pulling, okay, as physically shown here, pulling the O minus towards itself. And what really happens is the bond is weakened if the M2 plus have a strong pulling power, a strong polarizing power. So the higher the charge density of M2 plus, the stronger the polarizing power, and the better it can pull O minus towards itself. So that is to say, once again, beryllium can pull O minus towards itself better than magnesium, and so on and so forth. And barium has the lowest polarizing power and therefore least chance of decomposing and therefore highest thermal stability. And congratulations on completing your Group 2 e-lesson. Following this, please proceed to finish the post-test and be reminded that on the 15th of September, Thursday, you will have your lecture test on Group 2. Have a wonderful break.